Hi everyone, and welcome to the video lecture on the physics background for the awesome workshop. So in this lecture, we'll be going into the questions, what is the physics behind the data? And we'll be learning the basic physics processes. So first up, we have our signal processes. So as we've discussed, we're searching for a Higgs decaying to tau leptons. Now there are multiple ways that this Higgs could be produced. So here I've shown on the left the gluon-gluon fusion mode of producing a Higgs, and on the right, the VBF, vector boson fusion mode. So we call this right plot GG to H, and the left plot QQ to H, because the left plot is taking gluons, making an H, and the right plot is taking quarks from your proton and making a Higgs boson. And these two processes are going to be simulated separately before combining them with all the other relevant processes. So we're going to have different samples present in our data. We should have a sample present for GGH and a QQH sample. And these are the leading order Feynman diagrams. And then our signature is going to be the tau. And so we're looking for the tau decay modes. The tau can decay to either a muon or an electron and two neutrinos. And all other decay modes are a combination of hadrons and a single neutrino. And if you follow this link to the PDG here, you find a full overview and the exact numbers. So this analysis is considering only tau lepton pairs, which one tau decays into a muon and two neutrinos, and the other decays hadronically. This is yet another way that our analysis is a little bit simpler than the official analysis, which considered additional decay channels. So that is how we would produce and then see the decay of a Higgs boson. But there are other processes that can produce muons and produce jets. So our background processes. Many processes can produce very similar signatures, like I said, muons and jets. So we need to take this into account when drawing conclusions. So besides the QCD multijet process, there are all of these different ways that you can make physics objects that would look like two taus. The first being which is you could just literally produce two taus, but this time it's from a Z boson decaying to two tau leptons instead of a Higgs. So we call this the Drell-Yan because we're seeing a quark-antiquark annihilation in creating our Z boson. And it's decaying to two tau leptons, exact same as the Higgs boson. So it's very difficult to distinguish this from a signal. You might expect that this is one of the dominant backgrounds because Z's are going to be produced at an enormous rate in the LHC, and we have two genuine tau leptons in this background. Other than the Z boson decaying to two tau leptons, it can also decay to electrons and muons. So this process doesn't contain genuine tau leptons, but you could mistakenly reconstruct a tau. So there are objects that are likely to be misidentified as a hadronic decay of a tau lepton, like electrons or jets. So other big fuzzy objects in our detector with a lot going on. And if there are other leptons present, there could be a muon additionally present in addition to jets. We could identify a muon correctly as being from some hard scattering process and some decay of a Z. But then if there's also a lot of hard jets in the event, you might think that some of these jets are from a tau and think that this is a Higgs decay. Additionally, there's the process W plus jets. So W bosons are also frequently produced at the LHC, and they can decay into any lepton. If a muon from a W boson is selected with jets, a similar event signature can occur. So just like we had a muon from a Z plus some random jets or electrons or other other processes, you can see the same thing with W leptons, or sorry, W bosons. So this process can be suppressed by a cut in the event selection on the transverse mass of the muon and the missing energy. And this is done in the published CMS analysis. So there are additional ways you can cut backgrounds that we are not going to discuss in any more detail here. Then we have TT bar, or top anti-top pairs. Top quarks decay promptly and almost exclusively via a W boson and a bottom quark, and you can get misidentifications and get signal-like signatures in the detector similarly to the W process. However, identification of jets originating from the bottom quarks and the subsequent removal of such events is capable of reducing this background effectively. So we've gone through many of the backgrounds, and so far we've only seen one of them that actually has genuine taus. So this is something to consider on any collider experiment, especially at the LHC, that there's just a lot going on in every event, and there's a decent chance that all these other physics objects in your events could be misidentified as your actual signal. And finally, we have the QCD multijet background. And this is decays with a large number of events, which is pretty common at the LHC. There's just a lot of QCD stuff going on all the time. And misidentifications can be selected. Essentially, if you have enough jets, you might identify some of them as taus improperly. So simulating QCD is very, very hard. So we don't actually simulate the QCD multijet background the way that we particularly simulate every other background that I've discussed so far. We're going to do a data-driven estimation. So we're going to select tau pairs in the exact same way as the signal, but we're going to require taus to have the same charge. If we're looking for a Higgs boson, which should have charge of 0, if we find same sign taus, there's no way this could have originated from a Higgs boson. So we're using the magnets in the detector to distinguish the charge of the object. And if we know that these taus have the same charge, we should get something roughly like the same contribution you would get with opposite sign taus, but this time we know that there is no signal present. Now there still might be background present, but we know that there's no way this could have come from a Higgs boson. So if we take the data and we subtract off all of the background processes, this should give us an estimate of the remaining background, which is the QCD multijet background. So we take data, we subtract off everything, Z to tau tau simulated, Z to 2 leptons simulated, TT bar, W plus jets simulated, all these other backgrounds. We subtract them off the data, and we get an estimation for the QCD multijet process for same sign taus, and then there's a way that we can extend this into the region where taus are no longer the same sign. So that's the physics overview of what's going on. There's a lot of actually really interesting physics going on between all of the different processes we need to simulate, between multiple signal and background processes, and a data-driven estimation. And as we've talked about this, we've tried to give you an estimate of the relative size of these backgrounds, and that this one Z to 2 tau background was the only background with genuine taus. And if you go back one slide to the introduction and you look again at these plots, you can see all these background processes identified on the plots and sort of their relative size. As expected, the genuine 2 tau background is really, really hard to cut, so we have a lot of it present, and it's our dominant background. And then, perhaps not surprisingly, QCD backgrounds are somewhat large as well, so you see a significant contribution of this pink histogram. And what's overlaid are the GGH and QQH processes. So these are not actually added up the same way that all these other backgrounds are added up. These are simply overlaid to show you the shape of the signal curve And these are actually scaled up quite a bit by 10 or 100 times because there's not a lot of data. So you would have to significantly scale up these two histograms in order to see them. Okay, and that concludes everything I have for the physics background for the awesome workshop. The next video will be the step 1 on skimming, and we will see you there.